You know.
So last time I had started this, and it's called the mapping theorem, and it'll lead up to the Nyquist stability criterion. And so we'll get started here. We have an arbitrary closed clockwise contour. Closed clockwise. It contains z zeros and p poles. In this case, as shown here, z equals 1 and p equals 2. 1, 0 enclosed, 2 poles enclosed. It doesn't pass through any of those poles or zeros. And then what we do is for each of the points on here, as you can see in this example there, several points on this contour, this S-plane contour here, we, for this given function, the rational function, we find the corresponding closed contour in the complex f of S-plane, this imaginary versus real. In this particular case, what we would have is, according to the mapping theorem, first of all, you can see here, according to the mapping theorem, n equals z minus p, 1, 0, 2 poles minus 1 predicts that we will have minus 1 clockwise encirclements about the origin of the FS plane, about the origin, which is equivalent to 1 counterclockwise encirclement, okay, about the origin. And this is, in fact, what you would get if you did this mapping. You would find 1 net counterclockwise encirclement about the origin. Here's an example we took for this particular function here, simple function, and this arbitrarily selected S-plane clockwise contour. We evaluated these various points here in turn, right? Starting here, going down in the clockwise direction, and we got this point here, followed by this point, and so on. And what you can see is that we have here 1 counterclockwise encirclement about the origin, and the mapping theorem predicts that we will, in fact, have 1 net counterclockwise encirclement about the origin. Okay. Any question about this? So what we want to do then is apply the mapping theorem, which is this n equals z minus p, to the determination of the closed loop stability, and that mapping theorem becomes what's called the Nyquist stability criterion. However, instead of evaluating n, we're going to be evaluating z. Z equals n plus p. Okay, and you'll see why that is true. Let me erase this now. And consider the control system. We have our standard feedback control system. We have G and H. Negative feedback, and the closed loop transfer function is equal to the C of S over R of S is equal to G of S divided by 1 plus G, I'll just call it GH, it's the G of S, H of S. And so this is actually a ratio of polynomials. I call, it's a G of S over this denominator, I called it F. Okay, it's the same F that I was talking about here as a general rational function. And so this is our F, and so the poles of the closed loop transfer function are the same as the zeros of the characteristic in other words, they're the zeros of the characteristic equation. Okay. Okay, so if we find the zeros of f, then we have equivalently found the poles of the closed loop transfer function. Okay. Now, GH is a rational function. GH is some numerator over denominator of S. And so, correspondingly, f of S, 1 plus GH, 1 plus N over D is equal to N plus D over D. And what this says is that the poles of the open loop transfer function GH are the same as the poles of the this function, this rational function f of s. The poles are the same. Okay. So now let's consider the specific contour of interest, S-plane contour regarding feedback control systems. It's going to be that contour is no longer arbitrary. It's going to go up the j omega axis, and it's going to enclose the whole right half plane. This is j infinity. This point is infinity here. This point is minus j infinity. It's a closed clockwise contour. Okay, and it should not pass through any of the poles or zeros of the function f. Okay, and so it's like that. And we'll see later in an example where there is a pole of f on the j omega axis. So what we have to do is route around it and yet enclose the whole right half plane. Okay, so like in your homework. So now you can see here this closed clockwise S-plane contour is the S-plane, right? That we're talking about. P, the number of poles enclosed by the contour is equal to the number, since this is enclosing the whole right half plane, this contour, P is the number of right half plane poles of that function f of s. And Z is equal to the number of right half plane. And before I write that, P is also equal to the number of right half plane poles of G, H, right? That's what we saw here. The poles of GH are the same as the poles of F. Okay, so we have that. The number of right half plane poles of F are the same as the number of right half plane poles of GH. Right half plane, because this is the desired contour that encloses the whole right half plane. Z is equal to the number of right half plane zeros of F of S. And so what do we want Z to be equal to? Remember, F is this 1 plus GH. It's the denominator of the closed loop transfer function, right? And so what would we like Z to be equal to for stability? For stability, right? Number of right half plane zeros of F of S, same as the number of right half plane poles of the closed loop transfer function. For stability, we want Z to be equal to 0. So this equals 0 for closed loop stability. Closed loop control system stability. And so to determine, so our task then is to determine Z. Okay. Well, first what we want to do is determine n, right? Because if we know n and p, then we know what z is. And this p here is the number of right-hand plane poles of GH. This is typically known. In other words, you're typically given or can find the open loop transfer function GH. So you know what the poles of GH are, and therefore you know what P is, right? You know what P is. So we kind of check this off. We know what P is. What we need to do is find N, okay, in order to find Z, okay? So, and remember, N in this case is the number, the net number of clockwise encirclements about the origin of the FFS plane contour. In other words, what we need to do is for every point on this contour, find the corresponding point in the FFS plane, right? Just like here, for it's not every point, but for several points on this contour, we found the corresponding FFS plane and contour. And then what we did was count the number of encirclements about the origin, right? So here we map each of these points into the plane of the FFS plane. And whatever, okay? And we count the number of encirclements about the origin. Now, instead of mapping points from this S-plane contour to FFS, which is 1 plus GH, what we can do is map these points to the GH plane and just count encirclements about the point minus 1, right? Instead of the origin. And because you see GH is equal to FS minus 1, okay? So we'll be counting encirclements about the point minus 1 in the GH plane, right? So instead of this, we'll draw this. It's going to be shifted to the left by 1, okay? So it'll be kind of shifted to the left. And now what we're going to be doing is counting encirclements about that point there. Clockwise encirclements, the net number of clockwise encirclements. Okay, if it's negative, then that means we have some counterclockwise. What I should say, if we have a counterclockwise encirclement, then n is negative. Okay, so this is this mapping from this S-plane contour to this GH plane contour. The GH plane contour is what's called this contour here is called the Nyquist diagram. Okay, and what? Nyquist diagram. Okay, so then let's go through some examples. And we did one example the last time. And first we can determine the this simple example here. We're no longer interested in this contour that I had over here, okay? It's that contour over there, the S-plane contour. And now, the example that I have is this one. You have a 1 over S plus 1, and you have negative feedback. And clearly, C over R is going to be equal to G over 1 plus GH. It's going to be 1 over S plus 1 divided by 1 plus 1 over s plus 1 is equal to 1 over s plus 2. Very simple first order system. You can see that the pole is at -2, therefore this system is stable. Right? That's one way of determining stability, right? But that's okay if you have first or second order system, but higher order system, then it becomes more challenging. Okay. And now let's draw and what we did was draw the Nyquist diagram for this. Okay. In other words, for that S-plane contour that we see here, what we did was let S equal j omega. We went up the j omega axis, so naturally S equals j omega here, right? we set S equal j omega. So here we're talking about the GH. That's what we use, the GH, not the closed loop function, right? So the GH, and I'll just call it G because H is equal to 1. So G of j omega is equal to 1 over 1 plus j omega. And the last time we did evaluate this for values of frequency starting at 0 and increasing up towards infinity. And what we found was that the contour, for example, if omega is equal to 0, then GH is equal to 1, right? And so it starts here. And if omega increasing, we go increase omega to 0.1, 0.5, 1. Okay, let's try 1. We get 1 over 1 plus J1. That is equivalent to 1 over square root of 2 angle minus 45 degrees, right? So we got several points, and then this point with a minus 45 degrees at a radius of 0.707 is right there, and then we continued. We got points like that, so I don't need that. Okay, and this has a direction. It has a direction that corresponds to increasing values of omega. So it's like that. Okay. So what we've done, as omega went from 0 to infinity, the points in the GH plane, or in the G of S plane, H equals 1. Were like this, right? We had several points. And so finally what we have, and these are all, polar coordinates. So when in this region here, the magnitude of GH is very small and for high frequencies, and the phase is approaching minus 90 degrees. Okay, and now that we're at, what we've done is map this section here, call it section 1, into the plane of the open loop transfer function. You can call this section 1 prime. Okay, and then what we have to do is consider points on this infinite radius quarter circle. And the reason I say a quarter circle is that just as the points above the real axis are complex conjugates of the points below the real axis, the points there that you would get will likewise be complex conjugates. Okay, but in fact, if you're at an infinite distance, the magnitude of S is infinite, then what is the corresponding, looking at the GH, what is the corresponding GH?
0.
It's going to be 0. So they all those points on this infinite radius quarter circle map into the origin. And now once we have completed the mapping for the points above the real axis here, what we have to do is take the mirror image of what we have over there to get the complete Nyquist diagram. Okay, so the complete Nyquist diagram, and you can call this this here 2 prime. It corresponds to this whole semicircle here, okay? And you can call this 3. And 3 prime would be this. 3 prime. Okay. 1 prime, 1, 2, 3. That's into 1 prime, 2 prime, 3 prime. S plane, GH plane. This is the Nyquist diagram. Here's the -1 point. Actually, it's.
You got to shift it.
Sorry?
Do you have to shift it?
Oh, this is already shifted. This is the GH, right? What we said was the FS is shifted to the left to get
To get G.
GH. Okay, so it's already shifted, and so this point here was 1. So the -1 point is here. Clearly, this n is equal to 0. No encirclements about the point -1. And what is P, the number of right half plane poles of GH?
-1.
Right half plane,
Oh, 0.
0,
Yeah, it wouldn't be.
right? P is equal to 0, therefore Z, n plus P is equal to 0, therefore
Stable.
the system, the closed loop system is stable. Okay. And remember what we're using the GH, the GH, H equals 1 in this example, okay, for plotting the Nyquist diagram. We also use the GH to plot the Bode diagrams. We also use GH to plot the root locus. Okay. Now, any questions about this? Any questions? Clear? Okay. So let me go on to another example. A little bit, more complex. And this time I'm going to use the MATLAB. The example is this. We've got 1 over s plus 1, negative feedback. Okay. Yeah. Now this is second order system, and it's easy enough to determine the stability by finding the characteristic equation and solving for the roots of the characteristic equation, right? Or we can find a closed loop transfer function C over R is 1 over s plus 1 divided by 1 plus 1 over s plus 1. Right there, and so this is 1 over s squared plus s plus 1 squared. Now, the roots here are -1 and plus and minus the square root of 1 minus 4 over 2, which is equal to -1/2 plus and minus j square root of 3 over 2. And the roots are in the left half plane, system is definitely stable. So as an alternative, we want to determine stability using the Nyquist stability criterion. Okay, so we have our S-plane contour. Now, remember what I said was that the S-plane contour can't pass a condition on the mapping theorem was that the S-plane contour could not pass through any of the poles and zeros, right? So we'd have to route around the pole at the origin there. And so there's a pole, and so what we're going to do is route around it. And this, let me draw the whole contour. It goes up the j omega axis to j infinity. Okay, it goes around the whole S plane, the S plane. This is infinity. This is minus j infinity, and this is just break the axis. And here, what I have is any point on that little contour inside there is described by rho e to the j theta. And that's just polar coordinates, right? It's rho angle theta. Rho angle theta, where what we're going to do is let theta vary between 0 and 90 degrees, right? You see, if this little vector here is along the positive real axis, theta is equal to 0, right? This is theta in here. That's theta. And the size is rho, okay? So theta equals 0, it's horizontal. Theta equals 90, it's vertical, okay? And as theta varies from 0 to 90, it whips around like that, okay? And so you can call this segment 1, right? It's a segment from here to there. And then you can call that segment 2. And then you can call this one here segment 3. And once you have mapped those 3 segments into the GH plane, then all you have to do is take the mirror image about the real axis to get the complete Nyquist diagram. Okay, so here S equals rho e to the j theta on this, and then what we're going to do, in fact, is to let rho go to 0. Because why?
Because it's, I mean, we just want to like not pass through 0, but be as close as possible to that.
Exactly, right. And you want to enclose the whole right half plane. So if you let rho go to 0, you, in fact, this contour, the resulting contour that goes up the j omega axis and around, does enclose the whole right half plane. Okay, so in the open loop transfer function, we take the limit as rho goes to, here somewhere. We take the lim as rho goes to 0 of 1 over, I'll replace S now by rho e to the j theta, 1 plus rho e to the j theta, and I want to take the limit. So what is that equal to? Well, if you consider this factor there, when rho goes to 0, 1 plus rho e to the j theta just becomes 1. Okay, so that becomes 1, and this right here, what we're left with is this 1 over rho, when rho goes to 0, becomes infinite. And e to the j theta down in the denominator becomes e to the minus j theta up in the numerator. Okay, so this becomes infinity e to the minus j theta, where you remember that theta is varying between 0 and 90 degrees, increases from 0 to 90 degrees. And so now we can do the mapping. Pick up this. Oh, that. So I thought about it. Leave some room over here for me to work with. Pillage and then burn. Not the other way around. Okay, so while that's waking up, map. Start doing the mapping. And this is the GH plane. This is the Nyquist diagram, right? So this is pretty simple. When theta is equal to 0, you've got infinity. When theta is, say, 30 degrees, you've got infinity angle minus 30. 60 degrees, infinity minus 60, and 90 degrees, infinity angle minus 90 degrees. So, you know, if this point is at infinity, then what we're mapping is this, right? The 30 degrees, 60 degrees, and 90 degrees. And this is the direction corresponding to increasing values of theta. In other words, we're moving along this contour like that. And so I didn't put the direction right. The direction is like that, and like that. And as we move along this segment 1, we map this segment 1 prime. Okay. And now the next part is where we set s equal to j omega, right? Because we're moving up the j omega axis. So we set s equal to j omega, right? So next what we want is 1 over j omega, 1 plus j omega. We want to evaluate the g of j omega in terms of, and plot it. You know, we can plot, we can express this in terms of a magnitude and phase, and for every frequency omega, we can find the corresponding magnitude and phase. And so I have the top here. And in fact, I have the frequency response here. This is the M file. This is 1 in the numerator, s squared plus s in the denominator. That's s times s plus 1. Okay, and then I use Bode to get the magnitude and phase for various frequencies. And then, okay, I express it in dB, but that's not absolutely necessary here. We're not interested in the Bode diagram. We're interested in the Nyquist diagram. And then I print out the table there, and then I use the Nyquist command to draw to generate the Nyquist diagram through MATLAB. Okay, so what you can see here is I take frequencies starting very low. Can't take 0 because because that's right here, and I have to map. I have to route around that. So I take a small frequency omega, I find the magnitude and the phase. Forget about magnitude and dB. So what you see is that as the frequency increases from low to high, the magnitude is going from high to really low, okay? And the corresponding phase goes from minus 90 to minus 180, okay? So you can plot points, and that's what you need to do on your homework, right? This magnitude, that phase, that magnitude, that phase, magnitude, phase, and so on. But notice one thing, that the range of magnitudes is very large. It goes from 10 to the minus 4 up to 10 squared. That's a factor, that's 10, a million. Okay, and so you can't plot it precisely, but you can still get the information that you need, namely n, the number of closed clockwise, the number of closed
Clockwise
encirclements. The number, what is it? The net number of encirclements about the point minus 1 in the GH plane. Okay, so if you map these points here, and keep in mind that this point down here is minus j infinity. What you can kind of piece together what it would look like is this. It would come in like that. Okay. Why is that? You see, very large angle minus 90. So very large angle minus 90 would be a point down here somewhere. Okay.
Does that have to do with how it like goes around the zero without actually touching, or does that just the other diagram?
It doesn't have anything to do about
With that specifically, no.
Doesn't
Okay.
have to do anything about that because we're moving up the j omega axis.
This is the interpretation in the okay. Got it. They're two different ones, yeah.
Right. So we finished segment 1. We're on segment 2 where s equals j omega.
Mm-hmm.
And that's what we have here. And I generated a frequency response, right? So, you know, a magnitude of 50 angle minus 91. So you can see that the phase is approaching minus 180. And the magnitude is very, very small, becoming very, very small. So you take point, say, minus 135, where the frequency is 1, the magnitude is 0.707, and phase minus 135. So it's kind of like this, minus 135 somewhere in here. And this, the length of that vector would be 0.707. Okay. And then you can plot more points, minus, let's say this point here, that the magnitude is 0.2 now, and the phase is minus 153. So 0.2 is smaller, and the phase is larger in the negative direction. It might be somewhere in there. Okay. So, yeah, and this is the direction, right? So the direction is continuing. It hasn't changed direction. Okay. Now, what we have done is map the points on segment 2 into segment 2 prime. Okay. And now all we have to do is map segment 3 into the GH plane. So, can you tell me what would where would the mapping be in the GH plane?
Origin.
Origin. Why?
Because that mapping was infinite. The magnitude of S was infinite. So you plug in infinity for GH, you get 1 over infinity times infinity plus 1, which is 0.
Yeah. Right. So the one you can forget about. So it's basically 1 over S squared.
S squared, which is
Yeah.
0.
And so this is 1, 2, I call it 3 prime. Okay. And now that you've got that, just as this down here, this segment of the contour is the mirror image, and it's the complex conjugate of the above points. We take the mirror image about the real axis here. Something like that. It's, what do you call it, symmetrical. And then, well, the minus 1 point is here, right? Somewhere in there. It's not critical where exactly the minus 1 point is in this problem, because it's never going to hit the minus 1 point, right? And this is the minus 1 point. What's the conclusion about n? N is equal to 0, right? N is equal to 0. What is P equal to? Looking at the open loop transfer function, not the closed loop transfer function. What is P? No, P is the number of right half plane poles of the open loop transfer function. There are no right half plane poles of the open loop transfer function. P is equal to 0. Therefore, Z is equal to N plus P is equal to 0. Therefore, the closed loop system is stable. Now, what we're gonna find out is that if the root load, if the Nyquist diagram passes through the -1 point, turns out that in general, the system is marginally stable. Okay, marginally stable. Why? Well, what we're saying here, so this is the GH plane, right? So GH for a certain frequency, omega is equal -1. Okay? And therefore, 1 plus GH at that frequency is 0. And remember that this is what we called F of S, F of J omega. F of J omega was where we're setting S equal to J omega. And what that means, remember this is just the denominator of the closed loop transfer function. So what that means is that there is some frequency on the J omega axis, right? That's where S equals J omega. Yes, because we're talking about S equal to J omega. So for some frequency, the system is
has a pole in that frequency, right?
that
So there's a closed loop pole at a specific frequency.
there's a closed loop transfer function pole at that frequency. So it's on the J omega axis, right? And if it's on the J omega axis, what does that tell you about the system?
That's marginally stable.
Marginally stable. Yeah, right. And so that shows you that if the Nyquist diagram passes through the -1 point, we're dealing with, in general, with a marginally stable system. Okay. So I don't know if I have anything else on this this one here. This up here, this is the open loop transfer function, 1 over S plus 1. Want to go through another example? Yeah, here it is. Oh, one point here is that as the gain, if you put a gain K in this system here, what is the effect on the Nyquist diagram? What is the effect of a K on the Nyquist diagram? Well, you, sorry?
Because we really plug in infinities in there.
So,
Like if we plug infinity in for S on the bottom, it's still gonna equal 0.
right, but
It would affect the magnitudes over there.
it will affect the magnitude. If K is positive, it has no effect on the phase, right? And so it affects the magnitude. And therefore, all it's going to do is kind of expand this, right? It's not going to expand this section here because that's already at infinity. It's going to expand this section here, up above and below, right? And what it's going to do is going to be more like this, okay? Getting closer to the -1 point. For the system, it never will get to the -1 point, okay? Well, unless
K is infinite.
Unless K is infinite, but that's not practical, say. But let's take a look at the root locus for the system. The system here with a K in there, right? What does the root locus look like? So we have pole at the origin, pole at -1. The root locus looks like this. It's away, away, and it breaks away in the middle, one branch upward, one branch downward. What this shows you is that the system is always stable, right, for a positive value gain K. This shows the movements of the closed loop transfer function poles as the gain K increases. That K right there. And so the poles will, for a short interval, for a certain range of K, will be negative real. Right? And then as for a certain value K, there will be negative real repeated. And then as you increase the gain K, there'll be a complex conjugate in the left half plane. So it's always stable. All right. So that's another way of saying that it's never going to become unstable. It's never going to pass. Sorry, it's never going to become marginally stable. In other words, it's never going to pass through the point -1. Let's consider an example where it can. Okay. Third order system. This is a second order system. So when you move up to a third order system, you have the possibility of it becoming unstable. So that is our closed loop system. And first of all, I might draw the root locus plot here. Right, root locus, we have 3 poles at -1. Okay, so I have 1, 2, 3. 3. Okay, and the root locus will exist to the left. I should say a branch of the root locus exists to the left. And it is directed away from one of those poles, and how many asymptotes? Asymptotes? 3. The difference between the number of
zeros and poles.
Zeros and poles, finite poles and zeros. There are no finite zeros. So 3 asymptotes. And therefore, the angles involved are 180 over that 3. Okay, so that's
60.
plus or minus 60 and 180. Okay, so, and then the next thing you need to know is the breakaway, right? The breakaway is the sum of the pole locations minus the sum of the zero locations. There are no zero locations, so pole locations are -1, right? So summing those up, you have -3, and divide by that alpha, that number of asymptotes, you get -1. So that the breakaway is right there. Okay, and so and the angle of the asymptotes is 60 and -60. Okay, and then the question is, well, let's check to see if the root locus lies right on the asymptote. Okay, so you take a test point there. You draw a vector from each of the poles and zeros. There are no zeros. So from each of the poles, 1, 2, 3, they're all emanating from there. Okay, they all have an angle of 60 degrees. And so you apply the, what is it called? Angle condition. You got the zero phase. The phase due to the zeros is 0. minus the phase due to the poles is 60 plus 60 plus 60. And the question is, does that equal 180 R? And it does, okay, R equals minus 1. And therefore, what that says is that this is a point on the root locus, and therefore, this asymptote is actually a branch. Okay, and it's directed away. And what you see here is that there's the gain K of 5K. 5K, when we're considering 5K, that is the corresponding root locus. If it's simply 5, then there is a point on the root locus only. That this, for this, that corresponds to the closed loop transfer function poles of that system. Okay, so that's the root locus here. You can see that if the gain K is sufficiently high, that the system becomes unstable. Now let's take the K out there and plot the Nyquist diagram. The Nyquist diagram is done without the K. Okay. If you put the K in, what effect does that have? Like where,
Expansion.
yeah, it expands or contracts depending on whether K is less than 1 or greater than 1. Okay, so let's draw the Nyquist diagram now. And so we have this. This is the GH plane, or the G of S plane, more generally the GH plane. And the S plane consort. What does that look like? Notice that there are no poles on the imaginary axis, right? So we don't have to route around them like we did in the previous case. So it just goes up the J omega axis to J infinity, and circles the whole right half plane minus J infinity, and this is infinity. Okay, and it's a closed clockwise consort. And we have segment 1 and segment 2, right? 2 segments here. And so now, what we need to do right away now is to generate a frequency response. So this, like in your homework, I provided a frequency response in the first problem. You would generate your own frequency response for the other problems. And here, this is very close, and let's execute that. I have to wait. This is a previous problem, it'll go away. It's still kind of generating. Anyway, what we have to do here is set S equal J omega. So we have G of J omega is equal to 5 over J omega plus 1 quantity Q. So what we're going to do is find the expression for magnitude and phase, and for the various frequencies starting at 0. This time we can start at 0 because there is no pole. There is no pole to route around at the origin, and so we let omega increase from 0 to infinity, find the expressions for magnitude and phase, and plot those points. So So here we have the frequency response. This is the various frequencies, magnitude. Don't worry about magnitude in decibels, and phase. So it starts out with 5 angle 0. It starts out here. at 5. And then it goes down 4.92 angle minus 17, and so on. At the frequency of 1, it's 1.76 angle minus 135. And what you can see is that the magnitude is getting smaller and smaller, as you expect, and the phase is going down towards minus 270, right? Because at very high frequencies, basically you can throw away the 1 there, and you got 1 over j omega quantity cubed. What each j omega in the denominator contributes minus 90 degrees, so it's minus 270 at very high frequencies. And then you take a look at these points here. At the frequency of 1.39, the magnitude is 1, and the phase is minus 162. Okay. And when the frequency is 1.732, the magnitude is 0.625, and the phase is essentially minus 180. So this is what's called the 180 degree phase crossover point here. Okay. And so this is an example where the Nyquist diagram actually crosses the negative real axis. This point here is the 0.625, and the point, let me see, the 0.625 angle at minus 180. Okay. In other words, it's a vector from the origin and has a size of 0.625, and the phase is 180. Okay. So this is the direction of that Nyquist diagram. And you can see here at the very high frequencies, the magnitude is very low, and the phase is essentially minus 270. So it's like you can put, if you have a point like right here, the vector from the origin to that point has a phase of minus 260 something, and the magnitude is very small. And that's why it ends up down there, right there at the origin. Okay. And we take a look at this point here, at that frequency. We already did this one, right? At that frequency, we have, I want to plot that point there. It's, yeah, essentially 1, right? It is 1 at an angle minus 163. So, angle, and let's say that this is the unit circle. I know. And so being the unit circle, right, this vector from the origin to that point, this vector here it has a magnitude of 1. Okay, and the phase here is minus 162. Is that it? Yeah, minus 162.8. Okay. And so that's just the unit circle. This point right here would be minus 1. This point would be 1. This would be J1. And so this is a portion of the Nyquist diagram. What we've done is map this segment into the plane of the open loop transfer function. We got that. So this right here is segment 1 prime. And now, what about this segment here? Maps into the origin, right? So the origin here, that is 2 prime. And so the complete Nyquist diagram, let me get rid of that there. The complete Nyquist diagram, what we need to do here is take the mirror image. And this, again, what I'll do is just say that this point right here is 1 angle minus 162.8 degrees. So take this array this way. Okay, as well as the unit circle. 1 angle minus 162.8. Okay, and so we take the mirror image, right? So we have okay, and the direction is consistent. It comes around like this, comes around like that, comes around like that. And this is for the case where if you had a k in there, k would be equal to 1. Okay, k would be 1. Okay, is this system stable, marginally stable, or unstable?
It's a marginally stable because it passes through -1.
No, minus 1 is right here.
Oh, is right there?
This point right here is
0.622.
0.625, right?
Negative.
Minus.
It's stable.
In other words, at this frequency, 1.732 is 625 minus 180. So this is minus 0.625. Okay. And therefore, the minus 1 point is not encircled. Obviously, n is equal to 0. And p, what is p equal to? 0. No right half plane poles of the open loop transfer function. Therefore, z is equal to 0. Therefore, the closed loop system is stable. But remember that, like on this root locus, there is a, if the gain k is increased sufficiently, you will have right half plane poles. And the same thing here. If you put a k in there now, right? If you put a k, for example, if k, see k is equal to 1 right now. If you put k equal to 2, what happens to this diagram?
Would expand.
Expands out.
It would expand, right? In fact, this point here would become 2 times that, right? Which is 1.2, 1.25 or something. Which means what? That
And equal.
the minus 1 point would now be enclosed, right?
So now you have a range of k where it's stable.
You will have a range of gain k for which the system is stable.
Mhm.
In fact, if you increase this, if you increase by a factor of 1 over 0.625,
Again, marginally stable.
then this 180-degree phase crossover point will go through what? It'll go through minus 1. Alright, so what's called the gain margin is equal to minus 1 over alpha. And this point here is minus alpha, or right, minus 0.625. So if you take, what is the gain margin equal to, therefore? The reciprocal of 0.625, which is 1.6, okay? You could increase the gain if you put a k in there. You could make that gain k equal to 1.6, and what would happen to the system?
Because marginally stable.
The system becomes marginally stable. Okay? And so definitely if k is equal to 2,
It's unstable.
it's going to be unstable. How can we apply the Nyquist stability criterion, right? The Nyquist stability criterion says that z is equal to n plus p. It basically comes from the mapping theorem. What will n be in the case if k is equal to 2? you start anywhere here and count the number of encirclements of the point minus
Oh,
one.
there's two encirclements.
Keeping in mind that k is equal to 2, so this is double here. And so if you start here, you've got one encirclement, right? If you continue, you've got two encirclements, right? And so n is equal to 2, p was equal to 0, therefore z is equal to 2, which means that you have, what does that mean? It does mean that it's unstable, but z specifically is defined as
The
what?
number of right half plane zeros.
The number of right half plane zeros of the characteristic characteristic equation, right? Which is the same as the number of right half plane poles of the closed loop system, right? And so there are two right half plane poles of the closed loop system if the gain k goes to 2, which in terms of the root locus means that you'll have one up here and one down there. In the right half plane, it becomes unstable.
Why is P 0 here?
What is
The P here, why is it 0?
P is 0 because P is equal to the number of right half plane poles
Got it.
of
G.
F of F,
GH.
but which is the same as the number of right half plane poles of GH, right? Because it, 1 plus GH, which is F, has the same denominator as GH. Okay. So P is equal to 0. There are no right half plane poles. Now this should help you with your assignment. Okay. It's really applying the same ideas. Another thing we want to talk about is the what are called, here's the gain margin. I already defined that. That's the factor, in this case 1.6, by which you can increase the gain, at which point it becomes marginally stable, right? Because it will go through the point minus 1. Minus 0.625, if you multiply it by 1.6, it's going to be equal to minus 1. It goes through the minus 1 point. At that point, like we were saying earlier, GH of J 1.39 1.39, 1.732, right? Is GH is minus 1, right? This 180 degree phase crossover point, it just expanded, right? Which means that 1 plus GH of J 1.732 is equal to 0, and that 1 plus GH is equal to F of J, F of J 1.732, which means that the system would be marginally stable with a pole at J 1.732 and its complex conjugate minus J 1.732. Okay, would be marginally stable, and in fact, you can use the Routh-Hurwitz stability criterion to determine the
value of K.
The what?
For the value of K, for the marginal stability.
You can find K for marginal stability, and then you can use the auxiliary equation itself to find the frequency of oscillation.
So you're basically showing us another way right now to find the range of K for stability, right?
Yeah, you can use Routh's
Or this,
test.
okay.
you can use this
Mm-hmm.
Nyquist diagram.
And I assume there's advantages of each, right? Would it be
Yeah,
like
this is more graphical. The other
okay.
is
It's more numerical, yeah.
Yeah.
Like
okay. And this also leads us to what is called the gain margin and the phase margin.
mhm.
The gain margin is the margin of the gain that you can increase the system before it becomes marginally stable. In fact, it becomes marginally stable if you increase it by that factor. That's a measure of how stable it is, right? If that gain margin is larger, then you have to increase the gain by a larger value before it becomes unstable. Also, you have what's called the phase margin. The phase margin is that angle from the origin passing through this point here. Remember, this was a magnitude of 1 angle minus 162. So the phase margin is this angle with respect to the negative real axis. This angle in here is going to be 17 point something, 17.2. Okay. Subtract that from 180. What do you get? Something like that.
Looks right.
Okay, so the phi or phi sub n sometimes they call it, is 17.2. So you have 17.2 degrees of phase margin before it becomes marginally stable. And when the gain k reaches 1.6 here, that means that the Nyquist diagram will look like this. Minus 1 will look like that. And here you see the phase margin is 0, right? Is 0, right? This is the unit circle. Remember we drew the unit circle. And the Nyquist diagram goes right through the unit circle right there. The gain margin is 1, the negative reciprocal of that. And the phase margin is 0 when the system is marginally stable, right? And so the phase margin is 17.2. The gain margin was 1.6 minus 1 over alpha. And so these are both positive. You can also express this in terms of magnitude in decibels, right? And see, the gain margin in dB is 20 times the log of this gain margin that I have there, right? And so it's equal to 20 log of minus 1 over alpha. And then you can work that out, and that becomes minus 20 log alpha. Okay. So that 20 log alpha is the 180 degree phase crossover point. Let me show you one thing. Here's the Nyquist diagram generated by MATLAB. It's for k equals 1. Notice that it doesn't pass through the minus 1 point. These are the Bode diagrams of magnitude and phase. And so what you can do is you can get the gain margin and phase margin from the Bode diagrams, not only from the Nyquist diagram, but from the Bode diagrams as well. Okay, for the for the phase margin, you go to the 180 degree, the unity gain crossover point, right? The unit circle, to get the phase margin, we drew the unit circle, so you go to the unity gain crossover point, which unity gain means 0 dB, 20 times the log of 1 is 0, okay? The 0 dB gain crossover point there, draw that vertical line, and we measure the phase margin relative to the minus 180. It's this small mountain here, right? For the gain margin, you go to the 180 degree phase crossover point. Remember that this is 180 degree phase crossover point. And so all you have to do is take the negative of the magnitude, okay? And therefore, the negative of the magnitude, you get, as you can see up there, the gain margin is 4.08, right? If you take, this turns out to be 4.08, where alpha is equal 0.625, okay? So it might be useful to look at this next time when we get back. So start on your homework and other questions.